All right, I wanted to make a quick video about a question I was asked by somebody concerning uh, the COVID-19 the COVID-19 the COVID-19 vaccine. And so the question they asked, because they read an article that said if somebody gets the COVID-19 vaccine, uh, they will not get sick, but they can still spread the disease to other people, and so they can still be contagious even after getting the COVID-19 vaccine, and uh, thus they should still wear a mask, still do the following. And so you should still wear the mask, you should still social distance, and take all these precautions against spreading the disease. And they asked, so if we can still get sick, or if we do not get sick rather, but we can still be contagious, then how does that actually work? How is it that you can be immune to getting sick from the disease, but you can still spread the disease? And so this has to do with the types of antibodies. And so the 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 Pfizer, I don't remember how to spell it, Pfizer and Moderna vaccines, which are sort of the more popular ones, are both mRNA vaccines. And I've made a video on this already if you were interested in how that works. And this is injected uh, into the muscle. So it's injected it's injected with a syringe, and that goes into the muscles, and this will stimulate the production of IgG, so immunoglobulin G, and this is present in the blood and other bodily fluids. However, there are other types of immunoglobulins, which you can probably tell based on the fact that this is immunoglobulin G. There's another important one in fighting COVID-19, which is immunoglobulin A, and this is found in mucosal membranes, and so that would be places like the nose, and the pharynx, and so other places where COVID-19, where the SARS-CoV-2 virus can actually reside. And so when you get the vaccine, you are stimulating the production of this, but it is not stimulating directly the production of this. And so you can still end up getting virus sort of sitting around in the mucosal membrane, in your nose and pharynx, and therefore you can still spread this by breathing and coughing and things like that. And so even though you won't get sick because you have IgG, you can still spread it because eventually you will start producing IgA against COVID, and so this spreadability, this contagiousness, will eventually go away, but it will not be as fast as if they had like a nasal or oral version of the vaccine. So it is possible to have oral and nasal vaccines, and in fact there are companies working on a nasal version of the COVID-19 vaccine, specifically for this reason. So I have a few papers here. Um, I think I want to look at this one first. So this is looking at IgA, IgM, which is another blood type of immunoglobulin, sort of like A. It's just a little bit different. It has a different shape, and this is the first one that is sort of mobilized even before IgA. Uh, or I think I had that backwards. IgM is similar to IgG. These are the two blood versions, and this is the mucosal version. And so we see here, this is measuring the amount in people who are healthy, people who are interfering cases, which I won't get into that too deeply, but it just means that there are people who might have other types of IgA other than the COVID version that could possibly interfere with the test that they're doing. And one suspected case, so people who were thought to have COVID but were found not to have it. And then these are confirmed cases. And so you can see the IgA against COVID is much higher in the people who have confirmed cases. And we can see if we move over to the y-axis here, it's just a little under 1.5 million. And that is the same for IgM, which makes sense because, as I said, IgM is sort of a quick first response type immunoglobulin. But then we see the IgG here, and it's a little hard to tell because the graphs have different scales. So if we actually look over at the y-axis here, it's a little under 450,000 rather than 1.5 million. So this is only about a third the concentration as we have of the IgA and IgM. And so we can see that the IgA is very important for fighting COVID-19. And I have a few other papers here that show kind of the same thing. So this is looking at IgA and IgG. And once again, there's a difference in scale here, where if we go over here, this is using a different measurement. This is optical density rather than these RLU, this particular unit. And so it's not going to be the same. But we see this is a little under 10. We're over here for the IgG. This is only about 6 here, and we see that some of these cases even are outliers, going up as far as almost 35 of the optical density ratio. And we can see over here they look at the mild cases and severe cases for IgG optical density. And the IgA optical density for mild and severe cases, and the IgG for mild and severe cases. And we see, once again, if we look at our difference in scale here, in the mild cases, the IgA is almost up to 10 at the OD ratio. In the severe cases, it goes up to close to 25 here, with even some outliers going up as high as 35. Whereas our IgG here the mild cases is less than 5, and our IgG in the severe cases is just a little bit above 10 at 50 days after infection. And this is looking at kind of the same thing, but this is looking at neutralization of a pseudovirus, which is sort of a toned down version of the SARS-CoV-2 virus. And so we can see here, this is looking at neutralization of the virus for the IgG and the IgA here. And so these are not as clear cut as those other ones, but you can see here that the neutralization using IgG and IgA are about the same. And so this is the concentration on the x-axis here for the IgG and the IgA, and this is over here the 1 over IC50, and so IC50 is such that the lower that IC50 is, the more potent it is, the more effective it is. And so if we're taking 1 over IC50, then that makes it the opposite, because now as this gets smaller, then this whole thing gets larger. So if we are looking at that here, then we can see that that it gets larger as we go up the y-axis here. So higher concentrations leads to higher effectiveness, which is sort of what you would expect here. And it's a little bit clearer. There's a little, so the R equals 0.7 approximately, and that's just how well this fits a linear sort of data here, where R is only about 0.35 here for this one. But we can see that the IgA, if the concentration goes up, then the effectiveness is increased, and same with the IgG. And in this paper they also found, I think that was figure 6, that that dimer versions of the IgA are more effective than monomer versions. And so we can see that over here, the KD, which is similar to the IC50 in that it's measuring effectiveness, or in the case of KD, it's measuring sort of tightness of binding of the IgA monomer or dimer to the spike protein. And so that's looking at the viral spike protein, which has kind of a weird shape like this, and then we have our antibodies here, and so it's looking at how tightly this binds onto that. That's what KD is, and just like with IC50, as KD goes down, that's more tightly binding. And so we can see here that the KD goes down for the dimer, and so we are getting tighter binding with the dimer. Anyway, I think I'm going to call this good for the video. I just wanted to sort of talk about why this would be the case, that if you got the Pfizer or Moderna mRNA vaccine, which is injected into the muscles, why this would stop you from getting sick, but you could still spread the virus. I hope this was enlightening, and I'll see you in another video.